Hello everyone, welcome to my class. In today's class we will start chapter 4 and today I cover sections 4.1. So let me start the class right away. First, quick overview about chapter 4. In chapter 4 we study about the exponential functions and logarithmic functions. Note that exponential functions is 1 to 1, so it has an inverse, and the inverse of exponential function is the logarithmic functions. And exponential functions and logarithmic functions are called transcendental functions. So next, quick recall. Functions. A function is a relation that pairs each element from the first set, called the domain, with exactly one element from the second set, called the range. Note that this definition allows that more than one element of the domain to correspond to the same element of the range. Next, definition for one-to-one function. A function's f is 1 to 1 if every element in the range corresponds to only one element of the domain. In symbols, if you have same outputs, then we have the same input. Or if you have different inputs, then this gives different outputs. In the diagram here, in the first diagram, here the first set is a domain, second set is a range. Here is f is a functions defined from first set to second set. Here w is mapped to a, x is mapped to c, y is mapped to d, z is mapped to b. And in the second diagram, here 1 is mapped to 1, 2 is mapped to 4, 3 is mapped to 9, and -2 is mapped to 4. Since in the second diagrams, here we have two different input, 2 and -2, but we have the same output 4, so then this is not a one-to-one functions. But the first diagram is a one-to-one functions. Great. So now let's move on. Horizontal line test. If every horizontal line intersects the graph of a function in at most one point, then the function is one-to-one. Don't confuse this horizontal line test to the vertical line test. The vertical line test is for checking whether the graph represents a function or not, but here we are checking whether the graph represents a one-to-one function or not. Quick examples. Fx equals to 2x, the first diagram. Here the horizontal line crosses the graph of fx equals to 2x at only one point, so it's a one-to-one functions. Second diagram, this is the graph of exponential functions, fx equals to ex. This is again one-to-one. But the third diagram, this is the graph of fx equals to x square. Here the horizontal line touches the graph more than once, that means here is a two places, so then this violates our horizontal line test, so the graph does not represent a one-to-one functions. Awesome. By the way, we can restrict the domain of these functions and make it one-to-one, which I will discuss later. Awesome. Now let's move on. Quick remark. A function that is either increasing or decreasing in its entire domain of definition is one-to-one. You saw here, this is the increasing functions, this is the increasing functions, and if I only consider the left branch of this parabola, this is decreasing, then this will be one-to-one. If I only consider the right branch of this parabola, the function is increasing, then this is again one-to-one. But don't make a mistake here. But fx equals to x square defined on the entire real line. This is not 1 to 1. Great. I hope this makes sense to you all. Now let's move on. Now, inverse functions. If a function f is 1 to 1, then it has an inverse denoted by f inverse x. Here, this negative 1 on the inverse is not an exponent, and f inverse x not equals to 1 over fx. To find the inverse, one needs to reverse the order of operations with opposite operation. Let's see an example. Example 1. Next, example 1. Consider a function given by fx equals to 2x minus 3. This is a linear function. This is obviously 1 to 1, and hence it has an inverse. Let's observe these two tables below. First table for fx. Now here there are two columns, as the x column and fx columns. So for the x values, let's pick some negative, zeros, and positive numbers. So I pick negative 1 and evaluate the f at negative 1. So put x equals to negative 1 here. Then this gives you 2 times negative 1 is negative 2, and minus 3 is negative 5. Now similarly, pick x equals to 0, substitute in the given functions, then this gives you simply 2 times 0 is 0, then minus 3, so minus 3, and so on. So if I pick x equals to 6, then 6 times 2 is 12, minus 3 is 9. So this is the x values corresponds to the element in the domain, and this is the fx value corresponds to the value in the range. Now let me talk about the operations what we have in the given functions. In the given functions, for any given x values, we first multiply the x value by 2 and then subtract 3. Now let's do the reverse operations. So that means I showed here. So first let's go this reverse order. So subtractions, the opposite of subtraction is add. So first add 3, if that's better, add 3 to the x value, and then instead of multiplying by 2, and divide the new value by 2, so which is in this table here. So here, so in the x here, f inverse x here, so we pick x equals to negative 5. I'm just using those values here. Okay, I'm picking now negative 5, negative 3, positive 1, positive 5, positive 9. These are the values. And then it says add 3, so negative 5 plus 3 is negative 2, and divide by 2, so we have negative 1. Similarly, negative 3, add 3, so 0, divide by 2, so 0. Let's say the last one, the 9. For the 9, so add 3, so 9 plus 3 is 12, and divide by this new value 12 by 2, turns out to be 6. So that means here we pick our input from this range of this fx, and we get the values in the domain. So I hope this makes sense to you all here. So that's why I put this different color here. So that means if I write fx in order of pairs, then fx equals to this collections, the order pairs, negative 1, comma, negative 5, 0, comma, negative 3, 2, comma, 1, 4, comma, 5, 6, comma, 9. And for the f inverse, we got we switch this order pairs here. So negative 5 to negative 1, negative 3 is 0, 1, 2, 5, 4, 9, 6. I hope this discussion makes sense to you all. So the facts: if f is a one-to-one function with order pair AB, then its inverse is one-to-one with order pairs BA. You saw from these two examples, right? Great. And fact number 2, the domain of f is the range of its inverse, and range of f is the domain of f inverse. Great. Next, let's talk about algebraic method to find an inverse. Suppose the given function's fx is one-to-one, then follow the steps. First step, substitute y for fx, interchange x and y, solve the new equations for y. 4. The result gives the inverse functions. Just replace y by f inverse x. Then we're done. Now let's follow these 4 steps. To find an inverse of one-to-one functions. Example 2. Find the inverse for part A, fx equals to cube root of x plus 3, and B, fx equals to, this is the rational functions or functions in fractions form, 2x plus 3 over 1 minus x. Now, what are the steps? I just read here. First substitute y for fx, then interchange x and y, solve for y, then the result is the inverse of given functions. Great. So now let's follow the steps here. So solutions for part A, write y equals to fx. So then y equals to cube root of x plus 3. Second step, interchange x and y. So I distinguished by this color here. So y replaced by x and x replaced by y. I'm just switching x and y here. And then the next, I need to solve for y. So to solve for y, so let's take cube power to both sides. So the x cubed equals to the cube power to this 3 cancels. So then simply y plus 3. Now solve for y, means isolate y. So here's y equals to, bring this 3 to the left side, means subtract 3 both sides. So this gives us y equals to x cubed minus 3. We're done. And finally, replace y by f inverse x. So then this equals to x cubed minus 3. I hope this makes sense to you all. Now let's move to the second part, means part B. Write y equals to fx. So y equals to, this is given functions, 2x plus 3 over 1 minus x. Then the next step, switch x and y. So y becomes x, x becomes y. Here I just switch x and y. Then the next, I need to solve for y. So first let's cross multiply here. So that means there is 1 under x. Then I can multiply x times 1 minus y, which is here. So x times 1 x minus x times y is minus xy equals to 1 times 2i plus 3. So simply 2i plus 3. Now collect the y terms together. So that means bring this 3 to the left side and take xy to the right side. So here x minus 3 equals to 2i plus xy. I hope this makes sense to you all here. I subtracted 3 from both sides and I added xy on both sides. Then on the right side, let's factor the y outside, then 2 plus x inside the parenthesis. Then to find the value of y, divide both sides by this 2 plus x. So then y equals to x minus 3 over 2 plus x. and finally substitute f inverse x for y, then we found the inverse of given functions in part B as f inverse equals to x minus 3 over 2 plus x. I hope this makes sense to you all. Now let's move on. Quick asides here. Quick aside, let's talk about domain and range. So for the functions in part A, domain of f and range of f is everything, whole real lines. Similarly, the domain and range of f inverse is also everything, means whole real lines are. How about the function in part B? Here is the domain for these functions in part B. This is everything but not x equals to 1, so I need to avoid x equals to 1. So here, so the domain of f in part B is everything but not 1, and range of f is here all the y here values, all the y values, everything but not equals to minus 2. Similarly, the domain of f inverse is everything but not minus 2, and range of f inverse is everything but not 1. I hope this makes sense to you all. Now let's move on. Restricting the domain to create a one-to-one functions. So I think I introduced this idea earlier very shortly. That means if function is not one-to-one, then we can restrict our domains and make it one-to-one. So now here, let's explain with the example. In example 3, consider the functions. Here's a given function is fx equals to the x minus 4 outside is square plus 2. This is this graph here. It's the parabola opening upwards, whose vertex is at 4, 2 here. So it fails the horizontal line test. That's why it does not represent a one-to-one function. Here, by the way, the domain and range of this function of this parabola is, domain is everything, the whole real line, and range is from here, the y value is from 2 to above. So that means y belongs to close bracket 2 to the left side, and to the right side infinite. That means real lines are greater than or equals to 2. And observe that f is not one-to-one on its domain. So now if we restrict the domain in only at x equals to 4, so if we restrict the domain here, that means I'm only talking now on the right branch on this graph here, then we get a one-to-one functions. We get the one-to-one functions here. fx equals to the same functions, but our domain we restrict from real lines r to simply the intervals positive 4 to infinite. By the way, the range here doesn't change, still the range is 2 to infinite. So now let's find the inverse of these restricted functions. So now my function is here, fx equals to, this is the functions, and I restrict the domain for all x greater than or equals to 4. That means I'm only picking the right branch of this parabola. I hope it makes sense to you all. So now same idea to find the inverse. First write y equals to fx. So here's y equals to x minus 4 outside is square plus 2. Then interchange x and y. So y put x, for x put y, and copy other terms as it is. Now solve for y. To solve for y, let's bring 2 to the left side, subtract 2 from both sides. So x minus 2 equals to y minus 4 outside is square. Then take the square root both sides. So here y minus 4 equals to radical x minus 2. Here by the way we have plus minus, we have two choices, but by referring the domain of f we are picking the positive part. So here is y equals to then radical x minus 2. So then y equals to under the radical x minus 2, then bring 4 to the right side plus 4. And finally, replace y by f inverse x. So our inverse of this restricted functions, by the way, this restricted function is 1 to 1. The inverse of this restricted function is f inverse x equals to under the radical x minus 2 and plus 4 outside. Hence, the inverse of this restricted functions is f inverse x equals to under the radical x minus 2, then outside plus 4. Note, the domain of f inverse is 2 to infinite, including 2, and range of f inverse is 4 to infinite. Great. So now let's move on. By now you have the ability to find the inverse of your functions. Now let me give you a definition of the inverse functions using compositions of functions. So now inverse functions in terms of compositions, if that's better. If f is one-to-one functions, then its inverse exists such that each of the following holds. So here, first, f composition with f inverse at x gives us x for all x in the domain of f inverse, and 2 inverse of f composition with f evaluated x gives us x for all x in the domain of f. So now let me discuss about the diagram here. In the diagram, there is the first set, which is domain, second set is a range. Now function f is defined on the first set, then it takes x and returns fx, and f function is 1 to 1, and inverse of f is defined on the range of f, so that means f inverse goes from this set to this set. I hope this makes sense to you all. Now let me move on. Let's go example 4. Let's revisit questions 2 part A. Verify that the functions cube root of x plus 3 and x cubed minus 3 are inverse of each other using compositions. We found x cubed minus 3 is an inverse of this cube root of x plus 3 in questions 2 part A. Let me show it here. In questions 2 part A here. So now let's verify using these compositions. These two are inverse to each other. Let me scroll down here. So then what I need to show here in the solutions, I need to take the composition of f composite with g and g composite with f. If both composition gives me x, then by this definitions, these two functions are inverse to each other. Great. So now here, let's evaluate f composite with g. Here f composite with g at x equals to f of g of x. So here gx function is input function for f function. So what f does, f takes x and gives us cube root of x plus 3. Now here f takes gx, that means it follows this rule. So this gives me cube root of gx plus 3. I hope this makes sense to you all here. Now what is my g functions? Now my g function is x cubed minus 3. This plus 3 as it is, cube root as it is. Now here 3 cancels. So we have cube root of x cubed. This 3 cancels, gives me x. Great. So now let's do other compositions here. The g composite with f. This is same as g of f of x. So here's fx is input function for g. So then what g does? G takes x and returns x cubed minus 3. So now here g takes fx and returns fx cubed minus 3. I hope this makes sense to you all here. So what is fx? In the next step, fx is cube root of x plus 3, this 3 as it is, minus 3. There are a bunch of 3's here. I hope it makes sense to you all. So next, now this 3 and this cube root cancels. So I have x plus 3 and then minus 3 as it is. Now 3 cancels, simply x. So now in both these compositions gives us x and x. So now we verified these two functions are inverse to each other. Great. So now let's move on. Finally, let's talk about graphing a function and its inverse function in the same grid. The idea is the graph of f inverse is a reflection of the graph of f across the line y equals to x. Quick example, example 5. Graph these two functions fx equals to x square and gx equals to radical x on the same grid. So now in the same plane here. So we know these two functions f and g are inverse to each other. So that means the graph of these two functions are just symmetric about the line y equals to x. So this is the diagonal line y equals to x. We know y equals to x square is this parabola, right? Because I only picked the one branch here. This part I don't care. And y equals to radical x is this graph. Again, this part I don't care. So then here the graph of x square and radical x, they are symmetric about the line y equals to x. Great. I hope this makes sense to you all. Now we finish this sections 4.1. Thank you.